Let's now talk about the eigenvalues of the particle in a ring wave functions which distinguish the individual states. So we have, again, our particle in a ring model system where we have a particle which is constrained to this quasi one-dimensional surface here, which is just a ring of radius r around some origin, which we're saying here is along a z-axis. And the potential is 0 if it's inside the ring and infinity otherwise, thus it is constrained to only have non-zero values for the wave function inside the ring. So we have a wave function which only depends on the azimuthal angle phi, which goes around this ring from 0 to 2 pi. In this case, we have energy levels, which are h bar squared n squared over 2 times mass of the particle times the radius of the ring squared. And n is an integer, goes from minus infinity to plus infinity, and the absolute value of n tells you what the energy of the state is. So we have our states distinguished up to a double degeneracy for any state beyond the ground state. So the ground state is completely specified by the energy because it's the only one with the energy of the n equals 0 state. But then plus and minus 1 have the same energy, plus and minus 2 have the same energy, etc. And then we have our wave function, which is a normalization constant of 1 over square root of 2 pi times a complex exponential e to the in phi, depending on the integer n and the azimuthal angle phi. So, of course, our energies come from our Hamiltonian. Our Hamiltonian operator acting on our wave function gives us the Schrodinger equation, which is just h psi equals e psi. And as we said, we just have this determined by, this determines our states to within the absolute value of n. So if we have absolute value of n equals 0, then we see, plugging in n up here, that our energy equals 0. So there's no potential energy, and for the E equals 0 state, our psi is just our normalization constant because it's e to the 0, which is just 1. So our particle kind of isn't doing anything. Our particle for psi 0 is just staying wherever it is. It's isotropic density all throughout the ring, and it has no energy, and it's just kind of sitting there. But if we go to absolute value of n equals 1 or absolute value of n equals 2, then E in units of h bar squared over 2mr squared is 1, and then we see, just like particle in a box beyond there, quadratically increasing energy levels such that the transition difference between them increases linearly as you go up in energy levels. And we have these e to the plus or minus I phi for n equals plus or minus 1, e equals plus or minus 2 I phi. So you see the pattern there as we're going up. But these energies for plus and minus 1 aren't distinguished. The energies don't distinguish the individual states. We need another operator which distinguishes the state and gives us a distinct set of quantum numbers for every individual state. For any state that we have, we need to have individual eigenvalues or quantum numbers which also differentiate that state. And so we can do that with our old friend, the LZ operator, which we might remember from the rigid rotor and then also from the hydrogen atom. And this is minus I h bar times the derivative with respect to phi, the azimuthal angle. So this gives us the angular momentum around this z-axis here. And this follows the same type of eigenvalue equation that we had for rigid rotor and the hydrogen atom. LZ acting on our wave function gives us the eigenvalue h bar n times psi of n. So this means that, again, if we have our states of n equals 0, n equals, let's say this is plus 1, this is minus 1, and then let's say this is plus 2 and minus 2. Okay, so if we have, for n equals 0 state, again, our expectation value of LZ is just going to be 0 because n is 0. So it's an eigenvalue, so the expectation, it's an eigenfunction of LZ, so the expectation value is just the eigenfunction when you're in a pure eigenstate like that. So the expectation value is 0 for n equals 0. Again, there's no momentum. The particle is just kind of sitting there, and its density is spread equally throughout. It's not moving to the left or to the right. The particle is just sitting spread out in the ring there. Then we have up at the n equals plus and minus 1 states, we have eigenvalues of, for LZ, the expectation values equal h bar and minus h bar with n equaling plus or minus 1. So that means our angular momentum, if we say that phi is increasing this way, we have for plus 1, our particle is moving around. If we're looking down the z-axis here, so the plus z-axis is facing towards us, then we have the plus 1 state, the particle has angular momentum and it's rotating around counterclockwise. And for the minus 1 state, it has angular momentum and it's rotating around clockwise. So these states are distinguished by their eigenvalue. They have the same energy, but one is moving counterclockwise and the other is moving around clockwise. Same thing for the n equals 2 state. We have eigenvalues of plus 2 h bar for plus 2 and minus 2 h bar for the minus 2 state. So now it's moving around faster, twice as fast to be precise. The angular momentum is increasing linearly with our value of the absolute value of n. And in this case, we have that the plus 2 state is moving around to the right, and our minus 2 state is going to be moving around clockwise, so counterclockwise and clockwise again. So we see that we get a set of eigenvalues for each state, which is sufficient to distinguish them, because even though we have a degeneracy in energy between states with the same absolute value of n, our eigenvalues of LZ will either show positive or negative values, distinguishing whether it is the positive or negative state for that particular value of n.